This lesson is about polynomials and their properties. There's going to be two lessons, the first dealing with general properties and the second one focused more specifically on graph properties. First of all, the definition of a polynomial is often written this way. A polynomial takes the form a subscript n, x exponent n, plus a subscript n minus 1, exponent x exponent n minus 1, and so on, all the way down to a subscript 2x squared, a subscript 1x, and a subscript 0. We say that a subscript n can't equal 0, and we say that the numbers n are positive integers. This will be a polynomial of degree n. Degree refers to the largest exponent that we have. And a sub n represent coefficients. That's the most generic way that we can describe a polynomial. Some examples of polynomials could include some of the following. Make a little bit more space here. Examples might be something like f of x equals 5x exponent 4 minus x plus 4. This has a degree of 4 based on the largest exponent. It has a leading coefficient of 5, and the name of this one would be quartic. The name comes from the highest degree term. Another example might be something like 2x cubed x squared minus 5x plus 1. That's degree 3. Leading coefficient's 2 in this case. We call this a cubic. You also know quadratics, linear functions, and constant functions, and you can create lots of examples from your experience of those. The leading degrees would be 2, 1, and 0 correspondingly, and the leading coefficients are going to depend on your example. Now, there are some examples of things that aren't polynomials. For example, 1 over x minus 3. This isn't a polynomial because it actually has a negative exponent. If you think of the nature of reciprocal, that's an exponent of negative 1. Another example could be y equals square root of x plus 4, and this has a rational exponent of 1/2. So it's not a positive integer, so it wouldn't be a polynomial. Now, next thing I'd like to talk about is something that's often referred to as an end behavior of a polynomial. That refers to what happens as x gets larger and larger, or as x approaches infinity. I've got a couple of examples of cubics, a function x cubed and a function x cubed minus x squared plus 4. I've called them f and g. I've chosen some x values, and I'd like to look at specific values of f and of g. You could pause the video, substitute these as y1 and y2 into your calculator, choose a table of values, and look at the results. If you did, it would look something like this. Here's my y equals, or the function f, x cubed, and my other function, x cubed minus x squared plus 4. Now to control the table of values, do this. Second function window, and you want to have independent ask. So change that from auto to ask. Once you do, go second function graph to get a table of values, and it would be blank. And we get to enter different values and see the results. So if we entered the number 1, we would see that the functions behave fairly differently. If we entered the number 5, the functions behave differently, but the numbers 125 and 104 aren't dramatically different than each other. As x gets larger, you'll see now that the results are getting quite a bit larger, and they're also relatively close to each other. If I put an input like 15 in, the numbers again are still getting bigger, but they seem to be getting more and more like each other. If I put a number like 20 in, you'll see this result just continues to get larger but more similar to each other. And at this point, an input of 50, the numbers are actually quite close to each other. 50 is not even a very large input number. And remember, we were talking about results where x was approaching infinity, which is much bigger than this. I'm just going to paste that result in there and bring it over here. So you'll see that the behavior of these two things are really quite similar to each other. And the reason I say that is to make out the point that as x approaches infinity, this would also be true for negatives, by the way, so I could really say plus or minus infinity, the function f of x behaves essentially the same way as the function g. So what we learn is that smaller degree terms like x squared and constants and so on really don't have very much impact on the results compared to the largest degree terms. This is one of the reasons why polynomials are named based on the largest degree term. Now, some other attributes and habits of things that that happen. Actually, I'm going to pause this and just fix my screen here. All right, I'm back with you. I've fixed up some stuff that moved around. I'd like to generalize the effect of the exponent n as well as the leading coefficient on a function. Now, there's two different things that can happen. N could be an odd number or n could be an even number in the exponent. So f of x, x to the n, or negative x to the n, let's look at the sign effect for odd and for even functions. Now, the domain is real in every case. For all polynomials, we can put any number in for x. The range, when the function is odd, the range will be real. A negative in gives negative out, positive in gives positive out. However, when n is an even number, your range is going to be restricted to just positive values in this case, or just negative values in this case. Think of things like quadratics, which have degree 2, which is even. They either open upward or open downward, and it restricts the range values. Now, what you may not have considered in the past is this large x value behavior, or end behavior. As x approaches infinity or negative infinity, what happens to the y value? Well, if the function is odd, it will approach infinity if the coefficient is positive, but it will be negative infinity if the coefficient is negative. As I approach negative infinity, I get negative output or a positive output. You may want to pause and think about that and consider something like y equals x cubed as an example. For this one, y equals x squared would serve as a good example. You could put them on your calculator and see how these things are true. Now, for an even function, as x gets large and positive, the result is positive. Even if x is negative, the result is positive infinity. However, if there's a negative coefficient, the result is negative infinity. It gets larger as it goes downward. Again, consider negative x squared compared to positive x squared and see the effects of those. Next up, the zeros of a polynomial. Zeros are also called or referred to as x-intercepts. Now, a polynomial degree of n will correspond with this number of zeros. The minimum number of zeros could be 0. The maximum number could be n when n is even. Again, think of something like y equals x squared or similar. If n is odd, for example, something like y equals x cubed, you will always get 1 0, and you may get as many as n. Here are some examples graphically of what that looks like. Here's an example of a degree 2 with no zeros. Here's an example of a degree 1 with only 1 0, or 2 of the same 0. Here's an example of a degree 2, again even function, with 2 x-intercepts or 2 zeros. I'll refer to these as A, B, and C. Now, when it comes to odd functions, I might have something like this. I could have something that just crosses the axis one time. I could have something that crosses the axis one time, comes back, just touches and carries on, which is actually a repeated x-intercept. Or I could have something that crosses the axis, comes back, and comes back yet again, for example. All of these are degree 3 examples, or cubics. I'll call them D, E, and F. Now, there's a term you need to know called multiplicity. And multiplicity refers to repeated x-intercepts. And it happens when you get this effect like B has, where you really only touch at one place. See, that might correspond to something like y plus, or rather x plus 2, I should say, in brackets, all squared as a function. That actually has x-intercepts of -2 and -2, two of the same value. So we would say it has multiplicity 2. B has this as an example on these graphs, and E also exhibits this behavior, the way that the graph comes down and comes back. There's a repeated root, or a multiplicity of 2 in this case. Now, all of these statements are equivalent. Again, you may want to pause this and just have a look at these statements. They all mean the same thing when it comes to zeros or x-intercepts, and it corresponds to roots. Some examples of working with zeros. Here's two examples. We'd like to find the zeros of these. Now, the 0 is a place where the y value is 0, if you look at option 5. A comma 0 is an x-intercept. Or 3, x equals a is a solution to f of x equals 0. So imagine putting 0 here, and what I can do in this case is factor out of 4x, which leaves x squared minus 1, which in this case itself can be factored into x plus 1, x minus 1. This has 3 x-intercepts, and they are x equals 0, plus 1, and minus 1. This next example, what we can do is something called factoring by grouping. The first two terms have x squared in common, leaving x plus 2. The last two terms have 3 in common, leaving x plus 2. That leaves us with the factor of x plus 2, the remainder of x squared plus 3. And if I set this equal to 0 to get x-intercepts, I find that x equals 2 is the only x-intercept. X squared plus 3 can't be factored, doesn't have any solutions for us. So both of these are examples of cubic functions. The first one has 3 zeros, or 3 x-intercepts. The second one has only 1 0, or 1 x-intercept. One more thing to tell you about in this video, and that's something called turning points. A turning point refers to a place on a polynomial graph where it changes direction. An example you already know of is the vertex of a parabola. The number of turning points, plus 1, is the minimum polynomial degree. Looking at this graph, I have a turning point right there, 1, a turning point right there, 2, 1, 2. Therefore, the minimum degree of this polynomial is 3. You try this one. You should find that the minimum degree is 1, 2, 3, 4, 5, 6. All right, you may want to review some of this before you work on the lesson, and there is a follow-up lesson to this that will refer to graphing techniques and graphing information.